So let's take a look here at example number 1. We'll try to figure out how I can actually go ahead and attempt to calculate the antiderivative here of my given function x cubed times the cosine of x to the fourth plus 2. Now again, I need to remember that I have that list of integration techniques that we talked about at the start of the last video. I should always be checking first to see, is this a derivative rule that I already know from earlier in the semester? Or can I use any algebra to try to simplify this? And if I can't do one of those, then maybe coming to the idea of a u sub is a good option. So let's take a look. Is this a derivative rule that we learned earlier this semester? Nope, that is not a derivative rule that we know. I don't remember any derivative rule that spat out x to the third cosine x to the fourth plus 2. I don't even know of any good algebra way to deal with this, so a u sub might seem relevant. So now I have to go ahead and think about what I might want to pick for the value of u. Again, it's difficult. You're probably going to deal with a lot of trial and error here at the beginning. But the goal again is I want to pick something inside of here that I could let be u, so that its derivative would also appear, or at least almost appear, inside of here as well. So notice that there are probably some options that maybe aren't that great. I could maybe, for instance, start with u is equal to x to the third. And if I did something like that, I'd recognize, perfect, that's sitting right there inside my integral. Well, that would mean that then the value of du would be equal to 3x squared, du dx, the derivative of that would be 3x squared, and that would give me that du is equal to 3x squared times dx. So let's think about why this substitution here I claimed is a bad substitution. Why does it not end up being very helpful? Well, notice that would allow me to replace this portion of my integral with a u, but it says that now to get du involved, I need to have a 3x squared times a dx. And I don't have that. So what the heck am I supposed to do with this? Right? There's nowhere for this stuff to go. And I'll notice that I still have this cosine of x to the fourth plus u in here as well. And I never want an integral that's going to have a mixture of variables. I want to take this integral that used to have all x's and turn it into an easier integral with all u's. So I might need to try to think about how I could possibly readjust here. Notice the basic template still stays the same. Let's see. What if I tried something like x to the 4 plus 2? Right? I could imagine erasing all of this and plugging in a u. Well, the derivative of this would end up being 4x to the third. Now, I don't really have a 4x to the third times a dx inside of here, but notice that I could make one final manipulation to this equation. If I divided both sides by 4, I could state that x to the third times a dx is equivalent to a 1/4 times a du. And notice I do have an x to the third times a dx that could be replaced with a du and a 1/4. So to think about how all of these manipulations are going to come together, let's take a look at writing this out one line at a time. So this would say that my integral of x to the third times the cosine of x to the fourth plus 2 could be now kind of transformed in the following way. I'm still going to have my cosine, but the input of my cosine has been changed to a u. That's what I have here. I can also see that the derivative of that produces that 4x cubed. I rewrote that as 4x cubed dx is equal to du. And now, by dividing both sides by 4, I see that x to the third times a dx, which I have right here, can be replaced with a 1/4 du. Okay, so the substitution has been made, but I still have to make the determination of, is it helpful? I now have an integral that only contains u's, but is this an easy integral to work with? Well, I'm going to treat this like it's a brand new integral, and I'm going to go right back to my list of options. My list of options, remember, is this a derivative rule that I remember from earlier in the semester? Can I use any algebra to rewrite it? Or do I maybe need to try another u substitution? So let's see. Well, one thing that I know is that I could take this 1/4 and pull it outside of this integral, I don't know if this is ultimately going to lead me to an answer, but I know it's something I can do, so I'll try it. Now I realize I'm really just trying to find the antiderivative of the cosine. I'm asking, where did the cosine function come from? And that is a derivative rule that I do know from earlier in the semester. The derivative of the sine function would produce the cosine. To make it as general as possible, I'll put on the plus c. So I'm almost done. The last step that I'd have to do is to say, wait a minute, if I take the derivative of this thing, I certainly don't get back to here. But if I just replace u again with what it is equal to, x to the fourth power plus 2, I have myself a final antiderivative. And how can I know that my antiderivative is correct? Well, I just take the derivative. I'm going to go ahead and do that here for just this example, and I'll leave all remaining example derivatives and their calculations up to you to go ahead and confirm. But notice here that this is a super important step to be able, or to at least have the opportunity to take. So let's see here. If I wanted to calculate this derivative, I would start by saying, leave the 1/4 alone, then do cosine of stuff times the derivative of the stuff plus 0 because c is a constant. Notice here that my 1/4 and my 4 are going to cancel out, and I'm going to be left with x to the third cosine x to the fourth plus 2. Does it work? Yes! This is a really good antiderivative. Now again, you may not always select u to be the right thing on the first try, and that's okay. There's a lot of experimentation that happens here. So hopefully this gives you a little more confidence in what's happening, but we still have a couple more examples to get through in the next videos.